far cube reflectors, and they put them on the surface of the moon. And the idea was, we're going to use these for something important. And guess what? We are using them today for something important. We are taking these big lasers, just like these headlights, shining it at the moon on the moon. And when we do that, we can determine very precisely the distance from the Earth to the moon. We know how fast light goes. We now know how long it takes in time to go there and back. And so you can measure the distance very precisely to the moon. And there's talk recently about this. And the precision of that measurement currently is 0.8 millimeters. We know the distance from the Earth to the moon to within 0.8 millimeters, which is sort of remarkable when you think about it. All right, let's talk about spherical mirrors, and let's say a couple things, and then I'll give you a quicker question. So mirrors, of course, don't have to be flat; they can be spherical. Okay, and you're all familiar with these. You have them on your car, of course, on the right passenger side of your car. That mirror is not flat; it's curved, and it says on the car door, "No objects in mirror are closer than they appear." So when we think about mirrors, we can use the same idea of the law of reflection. But let's take a curved mirror. Okay, so a mirror curved like this is what's called a concave mirror. And light that comes in to this mirror will still bounce off according to the law of reflection, but it's the local angle that's important. So that ray will bounce off like so. But let's say we have another ray that's coming in near the bottom. It sees a different surface. It's going to bounce off like so. This is called a concave mirror because it's like a cave. You can crawl into it. Okay, and it has this interesting property that rays that come in parallel are suddenly focused towards each other. If the mirror is bent the other way, then it's called a convex mirror. And this is the one on your passenger side mirror of your car. And now a light ray that comes in near the top will be bent up at a big angle. A light ray that comes in near the bottom will be bent down at a big angle. Okay? So this is the primary difference between these things. Obviously, a convex mirror, if you just flip it around and it's reflective on the other side, it would behave just like a concave mirror. Okay? So it's really sort of the same element. It's just what side are you hitting? Are you hitting something that looks like a cave, or are you hitting something that is bent back the other way, called convex? All right, Sean, so let's think about our spherical mirror. There it is. It was made from some sort of spherical object, right? You cut it out with a big mill or something like that. There is therefore some center to this thing, right? If I have this radius r and I sweep it out, I'm going to mimic this arc of this spherical mirror. All right. What does this mean for the rays that are coming in? Well, when a ray comes in here, it is, of course, going to hit the mirror and bounce off at the exact same angle as it came in at. But that angle is relative to the local surface, and so we have to worry about this angle right here. This is your theta I. If that's your theta I, then this is your theta R. Okay, and so the ray takes off at that angle, theta R, and we know that those have to be exactly equal. So, if those are equal, that means that it crosses something which is called the optic axis, or the optical axis. It means that it crosses the axis at a very particular point, and that point is called the focal point of the mirror. Okay? Likewise, if a ray comes in on the other side, it is also going to go through the focal point. This F is called the focal point. There is a focal distance associated with that, which is this distance right here, F. And that F has a very special relationship to the radius of curvature of the mirror R, and it's the following. F is equal to R over 2. So what do we mean by focal point? Focal point means where all parallel rays incoming converge to. All these parallel rays that came in bounced off the mirror, and they converge right at the focal point. Now, this sort of mirror is, of course, what you use in telescopes. And if I think about a distant star looks like a point. It's so far away that the rays coming in from that star are all parallel. When they hit the mirror, I want them to go back to a single point. Put my CCD or film right there, that will generate a point, an image of that star. If the mirror behaves really well, right, then all those rays will converge at that point. But if the mirror is not quite perfect, if the mirror, in fact, is made from a sphere, not a parabola, then it suffers from something called spherical aberration. Spheres are really easy to make. Why are they easy to make? Because when you go to the machine shop, everything works on rotational principles, right? You go to the lathe, it has a big cutter on it that rotates in an arc. And so it's really easy to make circles. It's hard to make parabolas. And that's why typical astronomy telescopes, cheap astronomy telescopes, have spherical mirrors. Because a sphere is pretty close to a parabola until you get very far out to the edge. And when you get out far to the edge, then you suffer from something called spherical aberration. And in fact, you're all familiar with this idea of spherical aberration, because that's what plagued the Hubble telescope initially. When they first built the Hubble telescope and they sent it up, you were very young, of course, but the pictures that came back from the Hubble telescope were totally blurry. All right, they were supposed to be nice, sharp pictures of stars, and they were just blurry. three spots, and it's because they had spherical aberration in the Hubble telescope. A few years later, they went up with some corrective optics, literally a pair of eyeglasses to put on the Hubble, and they fixed the problem. And the Hubble vision went back to good 20/20 vision, and now it can see into the farthest reaches of the universe. So it's important to understand that spheres and parabolas are the same near the axis. They get worse as it goes farther out. So let's draw an object axis. And let's put our spherical mirror right there. And now let's take an object. We'll put the object right there. The spherical mirror, of course, has a focal point. If the center is there for the spherical mirror, then the focal point is somewhere around there. We'll label that F. When we think about the rays coming off of our object, we know that rays come off in all directions, but there's a few that we're very interested in. One of those is the following. There will be a ray of light from the object that goes parallel to the optical axis. Okay, it's going to come towards the mirror parallel. When it bounces off the mirror, it's going to go through the focal point. Okay, and it'll just keep going on out. All right, so that's a very important one. The second one is rays going through that focus are going to come out parallel. And there's one more point, which is the following. If the center is there, then rays that come through the center just keep going, bounce off the mirror, and come back on themselves. Okay, let's label those three rays. This is ray number 1, this is ray number 2, and this is ray number 3. And let's see if we can identify the rules that we just wrote down for those three rays. So ray number 1 is the following. Parallel ray goes through the focus. Okay, and that's exactly what we did. There was a ray that came in parallel, it bounced off the mirror, and it went through the focus. What about number 2? Number 2 is really just number 1 in reverse. Rays through the focus go parallel. Alright, number 2 was this one that came right here. It went through the focal point, bounced off the mirror, and then went parallel back. And the final rule is this ray number 3. Rays through the center do not bend. Okay, this is image formation. And these three rules are important to understand because they not only apply to mirrors, they are going to apply to lenses once we start talking about lenses. So where is the image in this picture? The image is where the rays all meet. They started there at the tip of the object, they went out in all these different directions, and then they came back together right there. So that's where the tip of the object is. The base of the object is on the optic axis. Okay? So this is a nice way to draw it. When you draw the object and you put it on the base of the optic axis, its image still has its base on the optic axis. And so all you really need to figure out is where's the tip of the image. Okay? And so this is the final point. Image is where they meet. Now, when we have image formation like this, you have to classify it as either a real image or an imaginary image, a virtual image. Images are real when real rays meet up. Okay? In other words, could I put a piece of paper there and form an image on it because real rays are coming to meet up with it? Yes, those three converging rays all meet right there. Virtual image is when the dashed line rays meet up. And that means you can't form that image on a piece of paper. So when we were doing the flat mirror, we said where's the image? It's on the other side. But remember those dashed lines that went to form that image? That means it's a virtual image. There's no real light that got there. All the real light stayed on this side of the mirror. In this case, there is real light that went to form the tip of that image. Posted, it said the following. An object is placed 2 meters away from a concave mirror of focal length 1 meter. So, mirror to focus is 1 meter, but the object is placed 2 meters away, which is interesting. That would put us right at the position C. Right, remember, A is half of the radius of curvature, C is the full radius of curvature. So that's where the object would be. Where is the image? Okay, and is it bigger, smaller, real, virtual? Let's see if we can follow our lens rule and figure out exactly where it should be. All right, rule number 1. Parallel rays go through the focus. Okay, here comes a parallel ray. Goes through the focus. Okay. Rule number 2, rays through the focus go parallel. Alright. And rule number 3 is rays through the center don't bend. Well, I guess a ray through the center would be straight down on itself. That would be ray number 3. So let's label those and make sure everybody's on the same page. This is ray number 1, this is ray number 2, and this is ray number 3. And now where is the image? It's where they meet. That's where they meet. The image looks to be exactly the same size as the object. Here's our object, here's our image. Okay, so it's also real because there are real rays coming to form it, and it is inverted, which just means upside down, and so the answer is C, of course, real and same size. Okay, excellent question. Okay, let's talk about something called the mirror equation, and this is the mathematical tools for figuring out exactly where that image is going to lie. So let's draw our picture again, and this is our mirror. Out of focus, about there. And when we have an object, we know that it's going to form some image somewhere. We're not exactly sure where yet. This thing is our object. This is our image. There are some distances that we can measure here. One of them is this. Distance to the image. From the mirror, from the apex of the mirror to the image, what is that distance? Likewise, we can measure the distance to the object. Okay, from the apex of the mirror to the object, what is that distance? And then finally, we can of course measure the focal length, which is from there to there. So the mirror equation allows us to determine where that image is going to be located. And the mirror equation is the following. 1 over dO plus 1 over di equals 1 over f. And remember that f was equal to r over 2. Okay? This thing is going to help you determine where di is. So let's take a look at the last clicker question that we just looked at and verify that this equation is in agreement with that. In that equation, we had the following. We had that the focal length was 1 meter. But we also had that dO is 2 meters. Can we solve this now for di? Well, yeah, that doesn't look too bad, right? Let's take this equation and let's solve it for di. All right, so we've got 1 over dO plus 1 over di equals 1 over f. So let's move the dO to the other side. I got 1 over di equals 1 over f minus 1 over dO. And now I know all those numbers, so we can just plug them in. 1 over di equals 1 over f, which is 1 over 1, minus 1 over dO, which is 1 over 2. All right, 1 minus a half is a half. So 1 over di is equal to a half, and if I flip it back over, I get di is equal to 2. And that's exactly what we found on that picture a second ago. If the object was 2 meters from the spherical mirror, and the image was also 2 meters from the spherical mirror. In this mirror equation, all these numbers are positive if they are to the left of the mirror. So dO measured to the left is a positive number. Di measured to the left is a positive number. F measured to the left is a positive number. If you solve the equations and you end up with a negative sign for di, that means the image is on the other side of the mirror. It's on the right side of the mirror. Okay. And that'll happen when you start to get very close to the mirror. If we have an optic axis here, and we have a plane mirror, then we know that an object will have the length dO, but its image is on the right side, and it's to the right, and therefore di is negative dO. And so now if you go back to your equation, right, we had 1 over dO plus 1 over di equals 1 over f. We're going to have 1 over dO minus 1 over dO equals 1 over f, and if 0 equals 1 over f, the only option is f is equal to infinity. Remember that focal length is related to radius of curvature, and so you're really asking the question, what is the radius of curvature of a flat mirror? In other words, what saw would cut out a flat mirror? A saw that had a radius that was infinity. Okay. So when we saw the image being formed, it looked like it was smaller or as big as the object. Can it in fact be bigger? And the answer is yes. And so we can quantify the magnification. The magnification m is just related to the height of the image over the height of the object. And that is directly related to how far away the image is versus how far away the object is. So in the last example, when we had the object placed right at C, the image was also at C, but it was inverted. Negative 2 over 2 just means magnification of 1, but an inverted image. So if the magnification is less than 0, if it's a negative number, that just means the image is upside down, it's inverted. All right, let's talk about convex mirrors. Right now, we just covered concave mirrors, but of course you can have image formation with convex mirrors. Let's see how that works. Okay, so here's our convex mirror, and let's draw the center of it, which is about there, and let's draw the focal position, which is about there. Notice the focus is over here on the right side of the mirror now, which means it's a negative number. So if I put my object right there, how do I find the rays that are going to form the image? We do the same thing that we did before. We follow those 3 rules, except we have to remember that the focus is over here and the center is right there. So this says that rays that are parallel to the optic axis, are going to go through the focus. But this thing is a mirror, right? It's a convex mirror. So there's no real light ray that penetrates through the mirror. It becomes a dashed line. Okay, this was rule number 1. All right, if it's a dashed line, what that means is when you look at this mirror, it's going to look like it came from there. All right. What about rule number 2? Rule number 2 was rays through the focus go parallel. All right, there's the focus. How do I get to it? I go like this. I get to the mirror, and it stops becoming a real ray. It, in fact, becomes a virtual ray. And this is ray 2. I guess this one here is fine. Okay. That one looks good. Ray 3 is going to be the hard one to draw. Okay. And before we do that, let's talk about ray 2. Ray 2 bounced off and went there. Okay, so it looks like it came from there. And then ray 3 is the one that goes through the center. And if I go towards the center, off it goes. That's ray number 3. And now this is a little hard to see, but hopefully you can see that those 3 virtual rays all look like they are intercepting each other right there. Okay. This might have a better picture of that. Sometimes it's a little hard to see up here on the screen exactly where it's intercepting, but that should be about the right position. This is, of course, a virtual image, because there's no real rays that are forming it. It is also demagnified, because it's smaller than the object. And this is what they mean by the passenger side mirror. Objects in the mirror are closer than they appear because it looks kind of small, right? And there's that great scene in Jurassic Park where he's looking in the rearview mirror at T-Rex, and it says objects in the mirror may be bigger than they appear. Okay, and it is also upright as opposed to inverted. That's how you would describe it. And this sort of mirror also obeys the mirror equation, as long as you remember that stuff on the right side has a negative sign, stuff on the left side has a positive sign. Let's talk about this idea of going from higher index to lower index, and let's talk about something called total internal reflection. So in our pool, when we had an interface, and we took, let's say we take a flashlight, okay, and we take it underwater with us. Here's our flashlight. And we're going to shine it towards the surface. We know that that light ray is going to bend, and it will bend away from the normal. So there is the surface normal, and if this is water, and this is air out here, then this thing would bend away from the normal, so it bends like that. Okay? But what happens when I start to increase this angle? In other words, let's move my flashlight up to this position. And now let's shine that ray at the surface, and I'll try to do it in a different color. Where is the light going to go? Well, it again bends away from the normal, and eventually it's going to go right along the surface. And if I keep going, if I keep moving my flashlight up, eventually I'm going to get to a position where the light never leaves the water. Okay? I can't bend any further away from the normal, and so all the light does that, and that is what's called total internal reflection. Now, total internal reflection only happens when you go from high index to low index, and it happens when that transmitted ray equals 90 degrees. Okay? So let's see if we can write this out mathematically. We know that Snell's law holds. Ni sine theta I equals Nt sine of theta t. Ni in this case was water. Okay. Theta I is the incident angle, but at a very special angle called the critical angle. The transmitted ray is at 90 degrees.